Welcome to Spring LIB.
Hello everyone, today we're doing chapter 19, problem 18, and this problem gives us the substituted phenol here shown as A, and it asks us to determine if the pKa of this phenol here is going to be higher or lower than this regular phenol with a pKa of 10 using the substituent effect, which is known to be similar for benzoic acids and phenols. So what we need to determine in terms of pKa, so the question is pKa of A going to be higher or lower than pKa of this phenol group here written in black? So what we know about pKa, the lower the pKa, the stronger the acid. The stronger the acid, the more stable the conjugate base. And how do you get the stability from the conjugate base? Well, a few things. You can have a negative charge on an electronegative atom. You can have resonance stabilization of the anion. And you can also have inductive pull of electron density away by having electronegative groups or electron withdrawing groups in the molecule in close proximity. So let's see what we have here in A. So let's say we deprotonate this proton here. So then we'll be left with the conjugate base that will look like this. So we see that we have a negative charge on electronegative oxygen atom, so that's favorable. But there's no actual resonance stabilization that can occur. So the only other factor that can stabilize this is inductive pull of electron density away from this oxygen nucleus towards other areas of the molecule. But unfortunately, what we see is that because this is on a benzene ring, we actually have this alcohol group, which is actually electron donating to the benzene ring through resonance. So we can have a carb anion now being placed onto the ring, and then we have inductive donation of electron density of this methyl group or this carbon hydrocarbon chain towards a benzene ring. So unfortunately, even though oxygen is electronegative, it is not more electronegative than the negatively charged oxygen here. So if this OH group was changed with, let's say, a more electronegative group like fluorine, then yes, we would have electron density being pulled towards a fluorine nucleus. But however, because the identity is the same as oxygen, there's no difference in the level of electronegativity between them. So the overcoming factor is this electron donation that can occur through resonance by placing a full negative charge in the benzene ring on this carbon shown as here, and then also the donating group of this hydrocarbon, inductive donation of electron density towards the benzene ring here. So because of that, we actually have a very unstable conjugate base here because there's nothing stabilizing this negative charge. So remember, the lower the pKa, the more acidic it is, but compared to phenol, if it was going to be a deprotonated, it still would have that negative charge on the oxygen atom, like as an A. But now there's no hydroxide group and there's no hydrocarbon group to donate electron density in here. So in fact, this is going to be a better acid than this molecule A. So remember what we talked about acidity, the better acid will have lower pKa. So because A is going to be a worse acid, we expect the pKa of compound A to be higher than 10, making it less acidic.